Hello everyone and welcome to the problem Z pattern. This is a problem that will show us how simply and beautifully we can use recursion to solve a specific type of problems. So, let's read the statement together. We are given an integer n, which is a power of 2, and we are going to see why is that. And we need to return a square of length n, which is filled with the numbers 1, 2, 3, n squared. And the way we fill these numbers has to follow the Z pattern. The Z pattern consists of recursively traversing the 4 quadrants in the order upper left, upper right, lower left, lower right. So, I know the statement could be a little bit confusing at first, so don't worry if you didn't understand it. This is why I've taken these 2 examples and we are going to fill the squares together to see how it works, right? So, for the first example, I have as the input n equals 2. So I have to return a square of length 2, right? So 2 by 2, which is filled with the numbers 1, 2, 3, 4 in the way of the Z pattern. And what does the Z patterns tell us? It tells that we should split this square into its 4 quadrants. So the way I do this is very simple. This is how you split a square into its 4 quadrants, right? We have to traverse the upper left quadrant, which is this one. So what I'm gonna do is that I'm gonna continue the Z pattern. I'm actually gonna start again the Z pattern for this quadrant. So obviously I don't have enough cells to split it again into quadrants. And because we are left with a square of length 1, we can right away write the number, which is 1. Right? Then, what is the following quadrant? Upper right. So, the next quadrant will be upper right. In this one, also of length 1, so I don't need to split anything again. I'm going to write the value 2. Lower left, so the next value 3, and lower right, next value 4. And this is basically what we have to return, right? We have to return this 2-dimensional array, which consists of 1, 2, 3, 4. Awesome. Now, let's take a look at the second example, which is more, which will make more clear how the Z pattern works because it's a little bit more complex. So we are given a square 4 by 4, and what should we do to fill it? Well, follow the Z pattern. What does it say? Split my square in the 4 quadrants. This is what I'm doing. So I'm splitting it in the 4 quadrants. So we are having our quadrants, right? Which are now squares of length 2, right? Awesome. This is why the n from the input is given to be a power of 2, right? Because in order to be able to have like a valid Z pattern traversal, this pattern always splits the square, if it has, of course, length at least 2, in 4. And then in 4 again, and then in 4 again. And you can try, but you couldn't do that with like an n equals 5 or an n equals 6, because at some point, the left of the quadrants will be odd, and will be different than 1 and odd, and you won't be able to split it again, and you get stuck basically, right? So, getting back to our problem, I split my square into the 4 quadrants. The first one being upper left. That's what the problem says. The second one being upper right. The third one being lower left. And the fourth one being lower right. Awesome. Now, what should I do? I should start the Z pattern for each of these quadrants. So I'll first start it for quadrant number 1, of course. We have to follow the order. Now, when I start the Z pattern for this quadrant, because it's a square, which this time has a length greater than 1, well, guess what? I am going to split this again into 4 quadrants, right? So let me pick another color here to make this more clear. Let's choose green. Awesome. So what I'm going to do when I'm going to apply the Z pattern here is that first I'll split this square into its 4 quadrants, and now each quadrant is of length 1. right? So we can go right away in the order of them and fill them with numbers. So this is the first one, upper left, upper right, lower left, lower right. Awesome. Now, as you can see, we are finished with this quadrant. So what we have to do is go back where we had to deal with the bigger square and continue the z-pattern traversal, which says that after you finished filling the first quadrant with numbers, you are going to move on the second one. So, second one, this one, also a square of length 4. Let me pick another color for this because we are going to also split it into 4 quadrants. So look what I do. I split it into its 4 quadrants. And because now each quadrant is a square of length 1, I can fill them with numbers. And I continue, right? The last number was 4. So I continue. 5 on the upper left quadrant, 6 on the upper right one, 7 in the lower left one, and 8 in the lower right one. Awesome. Now guess what? We go back to the big square and continue with quadrant number 3. We again, of course, split it into its 4 quadrants. Let me choose another color for that, just for consistency. So again, split this in its 4 quadrants and definitely fill them with numbers in the z-pattern order. And lastly, go back to the big square and deal with the 4th quadrant. I'm gonna choose red for this one. Yeah, let's choose red. When we deal with it, we obviously split it again in its 4 quadrants and continue to fill with the next numbers, right? Each of the quadrants, which are squares of length 1. And this is the z-pattern square of length 4. We have to do this for each n that could be given in the input, right? So we need to come up with an algorithm to build this square and then return it. Think about how you can use recursion on this. So basically, the problem statement told us that the big problem consists of 4 smaller subproblems of the same type, right? In order to fill a square of length 4 in this way, I need to fill each of its quadrants. Sorry about that. All right, here we go. I need to fill each of its quadrants in the exact same way in the order they gave us, right? By the way, the order could have been any other order. That is not important. The important thing here is that starting from a square of length n, in our example of length 4, which needs to be filled with the values from 1 all the way to 16, right? From this initial problem, we are moving to other subproblems. And what are them? The first subproblem is, of course, the first quadrant, which is a square, of length 2, which needs to be filled with the values 1, 2, 3, 4. 1, 2, 3, 4. Then, the second subproblem is the second quadrant, also of length 2, which needs to be filled with the values 5 all the way to 8. The third one, you guessed, this one, another square of length 2, which needs to be filled with the values starting from 9 and going all the way to 12. And of course, the last subproblem, another square of length 2, which needs to be filled with the values starting from 14 and going all the way to 16, right? So, in order to solve the bigger problem 4 and the values from 1 to 16, we need to solve first all those smaller subproblems and then combine them together, right? In this problem, combining the subproblems together is basically doing nothing, because once we solved those subproblems, so filled the quadrants with their numbers in the way that they should be filled, then of course we don't need to do anything special or stuff like that. You are going to see that there are problems such as the merge sort or other divide and conquer problems in which it's not enough only to solve the specific subproblem, but you also need at the end to combine them in order to get the answer for the bigger problem, right? Here, you get the answer just by solving them, because in the end, every square, every cell in the bigger square will be filled. So, what this tells us is that definitely this problem will be solved recursively, because I need to do the same thing each time I start with another square, which needs to be filled with some values. I basically do the exact same things, but with different parameters, right? So, I do the exact same thing in the first quadrant, but I start from this cell 1, 1, right? The upper left corner, and I have to fill the quadrant with the values from 1 to 4. I do the exact same thing that I'm gonna do in the first quadrant, also in the second one. The only difference is that I start from this cell, right? And go and fill these 4 cells with the values 5, 8. Also in the third one, but I start from this cell and I'm gonna fill these 4 cells with the values from 9 to 12. So what you need to do every time when you are dealing with a recursive problem, or when you want to build a recursive approach to solve a specific problem, is think about what are the parameters, what are the numbers that identify that subproblem or that define that subproblem. And let me show you on this example what I mean by it. So, we are dealing with the big problem, filling out this big square. This big square could be identified by its upper left corner, which is here on row 0 and column 0, right? So the square that has the upper left corner on 0, 0, and also I need to know the length of the square that I'm going to fill, right? Because only knowing the upper left corner is not enough. I mean, could be the big square or could be this square, right? So I'm also going to need the third integer, which is the length, which for the big square is 4. So this is the first problem that I solve, 0, 0, 4. Now, in order to solve it, I'm gonna need to solve 4 different subproblems, right? The first one is filling this quadrant with numbers. This quadrant is identified by its upper left corner, which is also 0, 0, right? But this time, its length is 2. So see, the length is very important to differentiate the subproblems. Now, after solving this subproblem and basically having the first quadrant filled with numbers, we are going to need to move to the second quadrant and fill it with numbers. This quadrant is identified by its upper left corner, which is here on row 0 and column 2. So 0, 2, and of course has a length of also 2. Awesome. Perfect. Now, let's move to the third quadrant. It has an upper left corner here. Row 2, column 1, column 0, sorry about that. So row 2, column 0, and also a length of 2. And the last quadrant, the fourth one, which has the upper left corner here. So on row 2 and column 2, row 2, column 2, and length 2, right? Awesome. Perfect. And this is just the first 2 levels of the recursion, right? So from this one, I go and solve these 4. Then for each of them, I'm gonna go and solve their 4 subproblems. Let's take only one as an example. Let's take the second one, right? In order to solve the subproblem 0, 2, 2, So filling with numbers the subsquare that has the upper left corner in, 0, 2 is this one, sorry. In 0, 2 and has length 2, right? So this one, I need to first fill with numbers its first quadrant, which is this cell, right? So it is 0 and 2, row 0, column 2, and has length 1. After doing that, I'm gonna go and solve the next quadrant, which is this one. So 0, 3 is the cell, and also this square has length 1, right? So 0, 3, 1. Then the next one will be on row 1 and column 2, and also length 1, right? So I make another call of the function and say row 1, and say column 2, and say length 1, and the fourth one, of course, is on row 2, is on row 1, and on column 3. So let's make here a fourth one, right? Row 1, column 3, and the length of that subsquare is also 1, right? And here we have basically the stopping points, because when we have a subsquare of length 1, obviously we are dealing with cells, right? So we won't split anymore. You can't split a cell anymore. You just fill it out with the value that needs to be there, and that's it. Like the function stops, right? But the problem is, how do I know the value that's going to be there? For the big problem, which is 0, 0, 4, okay, let's say I know that it should be filled with the values from 1 to 16. But when I call each of these, when I solve each of these subproblems, as we said, a subproblem is defined by only these three integers, right? The coordinates of the upper left corner and the length of the square we need to fill. But I don't know with what values I should fill it, right? So how do I know that 0, 0, 2 needs to be filled with the values from 1 to 4? Or that 0, 2, 2, this one, needs to be filled with the values from 5 to 8? I don't. Because when I'm making the function, if only these three integers will be our arguments, right? The parameters of each subproblem, they don't give me enough information to know what values should I actually write there. Make sense? So, what we need to do is also store in an argument what are going to be the values that we have to fill that subsquare with. So, let me erase this and show you how this will change, right? So, for the first problem, for the big problem, again, I'm gonna have the square that starts in 0, 0 and has length 4, and also needs to be filled with all the numbers that start from 1 and end to 16. But I'm not gonna write the 16. You know why? Because I know the length. So, just think about it. If, let's say, you have a square of length L. So you have a square of length L, right? A square of length L definitely consists of L squared cells, right? So I know that in the square that I should fill, I have L squared cells. And the smallest value in that subsquare is going to be 1. So I can tell what will be the last one. Let's take this example, right? The length is 4. If the length is 4, this means that I'm going to have 16 cells in total in this subsquare. This is correct. And if the first value, the smallest one that should be in the subsquare is 1, and all the values are consecutive, right? Because if you've seen, in each of the sub-problems, in each of the quadrants, right? All the values that I fill that quadrant with are, of course, consecutive, are a range of consecutive numbers. So here I can tell that if 1 is the first value, then 1 plus the number of cells 16 minus 1 is going to be the last one, right? Think about it. If, let's say, you had 4 cells and the starting value, let's call it start, was equal, I don't know, let's just give an example, was equal to 5, right? So I'm gonna need to basically write 4 numbers in those cells which are consecutive and start with 5. So I know it's 5, 6, 7, 8. Those are the numbers. And as you can see, 8 is 5 plus the number of cells, right? Minus 1. 5 plus 4 is 9, minus 1 is 8, right? So this is a mathematical trick. It's okay if you decide to have 2 extra arguments for knowing this information. So I could have also have done something like this. I could have stored 1 and 16, right? So I know that I should fill the square that starts on the cell 0, 0, has length 4, with values starting from 1 and going all the way to 16. That is completely okay if you do. But trust me, the interviewer will be way more impressed if you just use this mathematical formula instead of having another argument, which of course, when you deal with recursion and might have like a lot of function calls, even one argument could like make a difference. Not maybe in this scenario where the arguments are integers, but in general, it is very appreciated, right? So just hold the start variable and you know that the end one, the biggest one that you are going to basically write on that quadrant, that subsquare, will be the start one plus the length at power 2 minus 1, right? Perfect. So each subproblem is now definitely defined by 4 integers. They are more than enough for me to know how to fill that square with numbers. And what will I do here? 0, 0, 4, 1. So I'm gonna fill the big square with the numbers 1, 16. Cool. What is the first subproblem I should solve? It's the first quadrant. So first quadrant is going to be 0, 0. What's the length here? 1, of course. And what's the start value? The smallest value that's going to be in this subsquare? It is 1. Okay. Awesome. Oh, sorry, the length is not 1, the length is 2. That's my mistake. Alright, the length is 2. See what we've done here? We know that we should fill the square with the upper left corner in 0, 0, length 2. So this one with all the values from 1 to 1 plus 2 at power 2, 4, minus 1. So from 1 to 4, right? Awesome. Then the second one, which is the second quadrant, its upper left corner is in 0, 2. Its length is also 2. And I should fill it with all the values that start from 5 this time, right? Because if I filled this one with the values 1, 2, 3, 4, the second one starts with the value 5. So starting from 5 and all the way to 5 plus 4 minus 1, which is 8, which is indeed correct. Awesome. Then the third one. Here, row 2, column 0, length 2, and the value should be, well, 1, 2, 3, 4, 5, 6, 7, 8. It should start from 9, right? So it starts from 9, and the last subproblem, which is this upper left corner. So 2 and 2. The length also 2, and the first value it will ever have is of course 13, right? Awesome. Now, let's take again this second subproblem and also split it in its 4 subproblems. And I'm going to show you exactly why this was needed. So, first subproblem here, right? So we are talking about this quadrant, right? First subquadrant, right, from it is this one. So row 0, column 2, row 0, here you go, column 2, the length is 1, and the value is 5. Awesome. Second one, what is it? Is this one, right? So row 0, column 3, length 1, and the first value is gonna be 6, right? And we have the other 2, doesn't matter. What I want to show you is that now, when we call our recursive function that's gonna solve the subproblem with this 4 arguments 0, 2, 1, 5, we are going to find out immediately that this is a stopping point because the length is 1. So this is a cell. And now the question comes, which value should I write now in that cell? So okay, I got to one cell. This is cool. I know that I now should write a value there, but previously, when we didn't have this extra argument, we didn't know what the value was. Now I know. And I know the value should be, of course, 5. Here also, when I'm 0, 3, 1, 6, I know the value from here should be 6. Right? So, again, if you didn't have the extra argument, you'd only knew what is the cell that you should fill out with a number right now. I only knew 0, 2, 1. Length is 1, so the cell 0, 2 needs to be filled out with a number right now. But what is the number? And the number is the extra argument, right? So what we are going to do is that we are going to build a recursive function which takes 4 arguments, and only knowing those 4 arguments figures out how to split that problem into 4 subproblems, and of course call the function for each and every one of them with their new parameters. And of course, if it's the case and the length is 1, the third argument is 1, hit a stopping point, fill out this value into that cell and stop the function, right? So let's actually see how to do that. All right. And here is our recursive function next to an example to really understand each line of code and how the function calls itself 4 times in order to solve the quadrants. So we have the function fill square, which takes 4 arguments, row, col, len, and first val. This function will fill the square that has the upper left corner in row and col. So this is the upper left corner, right? Imagine like the big square was like way bigger, and this is just a subproblem. So we ended up on the function call, row, col, len, first val, and this is the upper left corner, row, col. This is the length of the square. Obviously, I chose a square of length 4, but that's not important. It's just for a better visualization. So this function will fill out this square that starts in row col and has length len. It's going to fill it with all the values in the range first val and first val plus len squared minus 1, right? And let's see how we do that. First of all, because it is a recursive function and we have to make sure that it doesn't call itself for an infinite number of times, we need a stopping point. And as we've talked about, the stopping point is when len equals 1, because we know we are in a specific cell. So let's suppose that for this example, len was equal to 1. So I was in this cell, row col, and the length was 1, for example, right? What should I do? Which should be the value that we have to write here? Of course, it's first val, right? We have to fill that cell with every number in the range first val. So it's only one number, obviously, and that is the first val. So all we do is just assign first val to that cell in the num's 2-dimensional array. So let's suppose we have made that array. Obviously, you can have it globally defined, so we can access it from the function, or you can make it an extra argument. It's not important. That's not the thing we should focus on. But what we do in this stopping point scenario is that we assign the first val value to that specific cell. Else, if len is greater than 1, right, like it is in this example, then we need to find a way of expressing each of the 4 quadrants, right? Express each of them in terms of row, col, len, and first val. So we can call the fill square function 4 more times with the right arguments to make sure that it's gonna go and solve each of those quadrants. So what I did here is that, first of all, I made an observation, which is not hard at all. And the observation is that when you split a square of length len into quadrants, each quadrant is going to be of length len divided by 2, right? So each of the quadrants will be a square of length len divided by 2. And I noted this len divided by 2 with a variable. I stored this value in the variable new len, right? Just not to make this division operations for like 1,000 number of times inside here. Let's just have a variable, right? And the variable is new len. Then what I have to do is first solve the first quadrant. In order to solve it, as we said, we will call the fill square function. But we need to call the function with the arguments that are corresponding to this quadrant. So we have to think about this. This quadrant, right? What is its upper left corner? It's also row col, right? Always, the upper left corner of the first quadrant is equal to the upper left corner of the big square. So fill square of row and col. Awesome. What is the length? We just said new len, right? Which is len divided by 2. So row, col, new len. And what is the first value that should be written in this quadrant when we are going to fill it with numbers? Of course, first val, right? So we call fill square of row, col, new len, and first val. And when this function call finishes, we are sure that this quadrant will be filled with the right values, which are 1, 2, 3, 4. Let's say for this example, right? 1, 2, 3, 4. Awesome. Then we have to solve the second quadrant. So again, let's figure out what is the upper left corner of this second quadrant. It's this one. Okay, how can we express it in terms of the things we knew, the information we have, which is row, col, len, and first val? Well, obviously, the row of this upper left corner of this cell is also row, right? So fill square here in the second function call, fill square of row. Awesome. Now, the column of this cell is not equal to col anymore. It is this one. How can we express this column in terms of our information? For this example, it is col plus 2. But obviously, we can't write col plus 2 here, right? Because sometimes it's going to be maybe col plus 4, col plus 8. So don't fall in the trap of getting some small examples and writing constants there and saying that, all right, that col plus 2 is going to be like the right column for each example. Even if I had, let's say, a square which had length 64, right? That doesn't happen. That 2 actually means new len, right? And why is that? You can think about it this way. We start from col, and we are going to jump to the right and jump to the right until we leave the first quadrant, right? So here we needed to jump 2 times. Let's take a bigger example and see how many steps do we have to jump until we reach the desired column. Let's take, for example, an array of length 8. I'm gonna draw it and then come back. Alright, here it is. Please excuse my drawing skills, they are not the best right now, but as you can see, I've taken a larger square, which now has length 8, and I split it into its 4 quadrants. And let's see what happens here, right? So, yes, the first quadrant is indeed the same in terms of its arguments, right? So the upper left corner is still in row col, that's good. The new length is obviously new len, which is len divided by 2, and the first value is still first val. Now, for the second one, yes, the row is the same, but the column is now 1, 2, 3, 4 is col plus 4, right? So always take more examples, think about the general case, and don't write constants like just for the sake of it. So why is this 4 right now? And why it was 2 in the previous example? Because it is equal to new len. As you can see, the first quadrant has length 4. So there are going to be 4 cells one after another on the row, right? So what I'm gonna do is, in order to reach the first cell that's not in the first quadrant from this row, is that I'm going to go through all the other cells. So from col, I have new len minus 1 other cells, and I have to make one other addition in order to actually get on this cell, right? So this is why it's col plus new len, col plus the length of the quadrant. So I have row, I have col plus new len. What is the new length? New len. And what would be the first value? Is it first val anymore? No, as you can see, it's not. But that's a good question. What did we do in this first call? We have filled the first quadrant, right, with all the values that start from first val and go to which value? First val plus the new length squared, right? So just for the sake of an example, let's say first val is 1. If first val is 1, then when we made this function call, we basically said that the new length is what? 4, right? The length divided by 2, so 4, and first val is 1. So in this call, we have basically filled this first quadrant with all the values starting from first val, which is 1, right, in our example, and all the way to first val plus the new len squared. The new len is 4, so 1 plus 16 minus 1. So I have filled that quadrant with all the values from 1 to 16, which is indeed what will happen, right, when we do this. Perfect. This means that if all the values from 1 to 16 are here, and this is the second quadrant, then the first value in this quadrant is going to be actually 17. In the general case, of course, this is not 1, not always 1, and this is not always 1/16. But the first value that's gonna appear in this first quadrant is, of course, first val. That we know for sure. Alright. And the last value, what's it gonna be? Well, it is the formula that we have just said. It is first val plus the new len squared minus 1. So, if we have placed all the values from first val to first val plus new len squared minus 1 in this quadrant, obviously the first value that's going to be placed in the second quadrant is this last one plus 1. So first val plus new len squared. So this is where first val plus new len squared comes from, right? Then, if we take a look at the third quadrant, let's see, what is the upper left corner here? It will be, of course, this one, right here, right? So this one, if I was to fill it, all right, that's the upper left corner. Now, as you can see, the column is indeed col, but the row is not the same anymore. The row, just like we have done for the column for the previous quadrant, is going to be increased by 4 in this scenario, which is of course new len, right? So again, in order to get to the first row that's not in the first quadrant, I have to jump new len times. So for the third quadrant, I call fill square of row plus new len and col and new len, because of course that's the length of the quadrant. And what is going to be the first value that's placed here? Well, following the same line of reasoning that we have followed for this second function call, think about it. You have placed all the values from first val to first val plus new len squared minus 1 in the first quadrant. Then another new len squared values in the second quadrant, right? So what we basically did is that starting from first val, we have written exactly new len squared crossed 2 values, because we have filled 2 quadrants and each of them contain new len squared cells, right? So if from first val, right, let's call it FV, right, just to be shorter. If from first val I have written new len squared values in the first 2 quadrants, that means that the last value that I've written was first val plus new len squared minus 1. So the first value that's going to appear in the third quadrant is of course this one plus 1. So first val, oh, and this is, sorry, 2 crossed new len squared. Okay, yeah. So the first value that's going to appear in this third quadrant is obviously first val plus 2 crossed new len squared. And we can check it out. Let's again suppose that first val equals 1, right? New len equals 4. What happens? All the values from 1 to 16 are in the first quadrant. Then all the values from 17 to 31, I think. 17 to 31, yeah, no, from 17 to 32 actually, yeah. All the values from 17 to 32 are going to be here, and the value 33 is gonna be the first one to appear in the third quadrant. Let's see if it's right. What is 1 plus new len squared, which is 16, 16 cross 2, which is 32, 1 plus 32 is indeed 33. You can check on paper, you can try out this example. This is the right formula, right? So these formulas are a bit tricky in terms of, let's say, the arithmetic approach of it. But don't worry, when you solve these types of problems, take a lot of examples, do it on paper, and make sure that you really understand for small examples how it goes, and then generalize it, right? So that's the approach for it. Cool. And for the last quadrant, the fourth one, we have to see which is the upper left corner. Which one? It's this one, right? This is the upper left corner of the fourth quadrant. Now, what is the row? The row, as you can see, is this one. Is the same row than that for the third quadrant, right? So it's row plus new len. The column is this one. It's the same column as the one for this second quadrant, right? So it's column plus new len. So we have our upper left corner in row plus new len, col plus new len. We have a square of length new len, and the first value that should be there is first val plus free crossed new length squared this time. And why is that? Because again, if we started here with first val and have written new length squared values, then we start here with first val plus new length squared, here with first val plus new length squared cross 2, and here, after writing a total of 3 crossed new length squared numbers in the first 3 quadrants, the first one will be first val plus 3 crossed new length squared. Now, obviously, after having defined the function, what we have to do in order to solve this problem is just call it for our big square. And what we will do here is call fill square of 0, 0, n, and 1. And that's it, right? This function call is going to take care of everything and make sure that the whole square is filled with the right values. Now, let's analyze the time complexity of this algorithm. As in any recursive approaches, all we have to do is count how many times the function fill square gets called, and also multiply the number of calls with how many operations we do inside each distinct function call. First of all, let's count how many operations each function call does. We have an if statement, that's constant. We have an assignment, also constant. We have the corresponding else with also an assignment, which is constant. And afterwards, all we do is call the fill square function 4 more times, and of course do some computations for the arguments like additions, multiplyings, and stuff like that. All of these are constants, so we can conclude that each distinct function call, right? So remember, we don't take into account what this function calls do, as they are distinct from the parent one. Each function call is constant time. All we need to do is check how many of them there are. And let's take the example again and see it visually. So the first ever function call is the one applied on the whole square. So it is the function call with the arguments 0, 0. In this example, n is 8 and 1. Alright. Then from this function call, the function is called 4 more times for each of the quadrants, right? So 0, 0, 4, 1, 0, 4, 4, 17, 4, 0, 4, 43, and 4, 4, 4, 49. Perfect. Then, for each of these 4 quadrants, guess what? The function gets called 4 more times for each and every one of them. So, let's take only the green one and see what happens. From this function call, we have other 4 more function calls, right? And I'm not going to write the numbers or the arguments because that's not the point here. But also for each of these other 3 function calls, guess what? It's going to happen the same thing, right? I'm not going to write the numbers here, the arguments, because that's not the point. But for each of these 3 other function calls, guess what? It will be the exact same thing. Each of them are going to call the function from itself 4 more times in order to split it into quadrants like in this one. So for each of those, we also have 4 other distinct function calls. And then, as you can see, on the first level of the recursion, we had only 1 function call. On the second level of the recursion, we have 4 function calls. Each of those applied on squares of length now 4. So half the length of the original one. Now we will have 16 function calls on the third level of the recursion, all of them applied to squares of length 2. And you can imagine if I am to take this little quadrant here, let's say the green one, I'm also gonna split it into other 4 quadrants. So for each of these 4 function calls from here, right? So imagine these are 4 function calls, right? Okay. For each of them, I'm also going to call the function 4 times. 4 times, 4 times, and 4 times, right? So you can imagine that from each of the 4 function calls, right, that was previously here, from all these 4 function calls, on the next level of the recursion, we are going to have 16 total function calls. And this happens for each of those, right? So 16 and 16. Awesome. So, as you can see, what happens here is that if we take a look at the recursion tree, we basically start from one root, which is the first function call on the whole square. Then from this root, we have 4 sons, right? 4 other function calls from inside the parent one. Then for each of these sons, we also have 4 other function calls from inside the parent, right? And for each of those other 4, and so on and so forth. So we can get an idea of how many function calls there will be in total. And in order to get the idea, again, let's just take this example, right? As I said, on the first level, I have only 1 function call. On this level, I have 4 function calls. On this level, I have how many? 4 times 4, 16 function calls. On this level, how many? 4 times 16, 64 function calls, right? So what you can notice here is that on the last level of the recursion, the total number of function calls are equal to n squared. This is n squared, right? And this is expected because we are expected that at the end, we have a separate function call for each cell in order to place the right number inside it, right? So if we take a look backwards on this recursion tree, we can say one thing. The number of function calls on the last level is n squared. Awesome. What is the number of function calls on the previous level, right? On the level above? Well, think about it. What I said that from each parent function call, we have 4 distinct other function calls, right? So these n squared function calls are the result of n squared divided by 4 function calls from the level above. So on this previous level, like you can see in this example, 64 divided by 4 is actually 16. Awesome. Now, this n squared divided by 4 function calls from here are obtained from n squared divided by 16 function calls. So take the number and again divide it by 4, and that's the number of parent function calls. So we have an n squared divided by 16 here. As you can see, n squared being 64 divided by 16, it is indeed 4. And so on and so forth, right? Until we start to hit the second level of the recursion, which obviously always has 4 calls, then the first level of the recursion, which obviously has only 1 function call. So, in order to compute the total number of function calls our algorithm does, we need to find a smart way of computing this sum, or at least approximate it. Now, one way to do this is notice that n squared is the common factor of each and every one of those, right? So, we are going to end up with n squared crossed. The first one was n squared, so 1. The second one was n squared divided by 4, so 1 divided by 4, plus 1 divided by 16, and so on and so forth, until we reach 1 divided by n squared, right? Which is also a power of 4. So, awesome. Now all we need to do is approximate this sum. 1 plus 1 divided by 4 plus 1 divided by 16, and so on and so forth. This sum is actually less than 2. And this is the beautiful part. You might wonder, Why is that? Well, one kind of intuitive approach of seeing this is that look how quick the number get very small. I mean, from 1 to 0.25 to, I don't know what this is, but it's even smaller than that, 0.05, I think, or something like that. They get very small, right? But other way of looking at this is the following. For this sum to be less than 2, what has to happen is that all the numbers except 1, the sum of all the numbers except 1 has to be less than 1, right? So 1 divided by 4 plus 1 divided by 16 plus, and so on and so forth, 1 divided by n squared has to be less than 1. Well, for this to happen, the sum of these numbers except 1 divided by 4 has to be less than, what is it, 3 divided by 4, right? For this to happen. Now, for this sum to be less than 3 divided by 4, you can imagine the sum of all the numbers except 1 divided by 16 has to be less than a value that is not a lot smaller than this 3 divided by 4, and decrease it, and you are going to end up with something like 1 divided by n squared has to be less than a number which is way larger than that, right? So the rigorous mathematical proof of this is actually that this is a geometrical series, because the numbers always get multiplied by the same amount, which is 1 divided by 4. So 1 divided by 4, 1 divided by 16. And you can actually come up with a formula for this. There is a formula for the sum of geometrical series. You can Google it, but I think these two explanations are enough for you to understand that 2 is actually the upper bound of the sum. So this means that the total number of operations is going to be less than 2 crossed n squared, right? So if we have a total of function calls which is less than 2 crossed n squared, and for each function call we know that it executes in constant time, right? This means that our final time complexity is n squared, because we drop the constant. So our algorithm has a time complexity of big O of n squared, which is awesome, because if you think about it, you can't do it faster. You need to at least go through each cell and write a number in that. And because there are n squared cells, every time, no matter what is your algorithm, you will do those n squared operations, right? So big O of n squared is actually the optimal solution for this problem. And that's it, guys. As always, enjoy the coding, and I'll see you on the next one.